record on. There we go. There we go. All right.
I'm going to consent here. Okay.
It's what?
I was consenting. It said, this is
Oh,
being recorded. Do you want to leave?
Yes. Okay. So now we have to moderate our colorful language. So, no, in fact, it was our pandemic chats that stimulated this idea, because I was thinking, back when you and I were doing this, back literally 4 years ago, it was like, yeah, we're capturing all this. You and I are getting the information and we're moving things along. That's great. But somebody else might want to listen in on this stuff who has an interest in being out in the weeds. So that was where the initial idea came from. So it's not a podcast per se, but literally two scientists chatting over coffee, and you get to eavesdrop. That's it. That's literally the idea. So we'll see. Anyway, cool. So let's talk. What's the latest on the legs? What's your new news?
New news is we've been working on some stuff with Cole Corpenay and Amy Janes. They're two of my Amy's was at McLean for a long time. She's now at NIDA. Cole Corpenay was at NIDA, now is at McLean. And they were looking at an old data set of Q reactivity in people in nicotine dependent subjects. And this is an interesting study where they look at they show tobacco cues, and the strength to which you respond to these visual cues is predictive of whether or not you will end up being successful in quitting smoking, which is interesting. And so Amy's been working on this for a long time, and she has a lot of fMRI data for her Q reactivity task, and she was interested in looking at whether cleaning the data with Rapidtide would improve things at all in her measurements. So they were doing they did a resting state and then 5 runs of a Q reactivity task. And initially they had found that the strength of the response, or the strength of the connectivity in regions of the amygdala and insula, I think it was, mostly in insula, increased over time throughout the task. And they thought, oh, this is interesting. So they're getting more and more engaged with this task, and the connectivity is increasing. But then they thought, science is never this good to you, right? It's never that. That just seemed too much in line with what they had thought they would see. So they said, well, how does the connectivity relate to other parts of the brain? And they found the connectivity increased to other parts of the brain too, between the task runs. And in fact, so then they did sort of a global measure of connectivity, sort of, connectivity of everything to everything else. I think there's an AFNI program that does that, some sort of overall connectivity metric. And it increased throughout all of the runs. In fact, they started with the resting state run, and connectivity increased through that. Then they went to the Q reactivity runs, and it just went up and up and up and up. And they thought, well, this is weird.
So this, you mentioned this you gave that talk to the ICP network.
Yeah.
I watched.
Yeah.
And you mentioned it. In fact, I think, hold on a second, share screen. I believe I happen to have it. Yeah. Is that it?
That'd be the one. Yeah.
Look at that. How good am I? Preparation. Yeah, this was this I don't know, the LFO signal. So there's the strength, and that's run to run to run, and it just concatenates, just keeps going up.
Yeah, so what we did in this case is we split the so anyway, having seen this in this data set, we thought, is this unique to us? And then we started looking at everything we could get our hands on. We looked at HCP data, we looked at some of the Midnight Scan Club data, we had some other data sets from other places, and we saw this and this was actually it's interesting that you were mentioning this. I kept wanting to name this paper secular terms in neuroimaging time courses. But that's a sort of an obscure physics word, and I think we thought that would turn off neuroscientists. But anyway, there seems to be this secular increase in low frequency noise over time, and so we went through a lot of thinking about this, and sort of the first thought is some sort of artifact, right? Which was one of the things that prompted us to look at different.
You mean like scanning artifact?
Like
is not resetting, so you're getting a slow drift.
Yeah, we had talked about this. You and I had talked about, perhaps scanner heating or something. Um,
Yeah.
it
No,
didn't
that would
look
go.
like.
You always get a step. Whenever you see that, you'd get a step, a sawtooth, because it would
Yeah,
go
and
back with
and
the
we
on
did
resonance
in fact
adjustment.
see a bit of a sawtooth in some of the connectivity metrics.
Uh,
Now, so that was concerning. But we've since you and I talked, we've looked at this data a lot more in depth. And one of the things we found is that while this is on average true, that people increase linearly over time, or not linearly, but they increase over time. Um, it's not everybody. It's about 75 to 80% of the subjects have this increase. Some subjects don't. So that sort of argues that it's maybe not a scanner artifact. Um,
I have
it's
two ideas.
hmm?
I have two ideas.
Okay.
So if we go right back to the origins of the sLFO, the systemic low frequency oscillations, which I mean, down below, I'll post to videos and blog posts that people can read about it.
Mhm.
But we are fairly sure that it has at least three discrete components. So you've got the arterial CO2 being modulated
Mhm.
because you're not breathing uniformly. You've got the arterial SaO2 that Toshihiko also showed is non-stationary as well for the same reasons. So your minute ventilation is changing. And then you've got your Meyer waves, which I never fully understood, to be honest. But let's call that changes in blood pressure, right? Non-stationary blood pressure over time. And I've subsequently read that Meyer waves are strongly associated with heart rate variability.
Mhm.
Heart rate variability is itself strongly correlated with respiratory sinus arrhythmia. Then you would expect those to be somewhat coupled, right? So again, ventilation and blood pressure may have some shared power. So the two things or three things could be going. All three of those things could be going over time. You could be slowly suppressing your respiration rate because you've been laying down for longer. You could also be refluxing more CO2 because of the bore ventilation. And that would be subject specific to a first approximation because it would be maybe size dependent and um, how you've got them put in the head coil. And then, of course, the blood pressure itself
Mhm.
could be slowly drifting over, modulating over time as you get comfortable. So all of those, all three of those could be happening.
Yeah, so that's actually where we ended up going on this, is that we concluded, partially in response to, reviewers' comments and stuff.
Oh, this
Um,
is you've written a paper?
oh yeah, yeah, yeah. Yeah, sorry. So the
Send me.
we have a preprint up on bioRxiv, but we
Okay.
have a paper in review at Nature Human Behavior.
How did I
Uh,
miss that?
so
Oh
um,
no, wait, I did. Yes, I sent you comments on that, didn't I? It was a few months
yeah,
ago. Yeah,
yeah.
yeah. Okay, okay. I'm not completely living in.
We don't have another paper.
Okay, no, that one I do remember. I do remember that one. Yeah,
Yeah,
like 3 or 4 months ago, maybe more.
yeah, yeah.
Okay.
So what it seems like it seems to be a sort of over time your arousal level seems to decrease, which modulates your respiratory rate,
That-
which then leads to, we believe, an increase in the sLFO power.
yeah.
I mean that's and we actually, one of the data sets we have has also pupillometry data. Um, and so Taylor Bolt has a preprint from last year where he's looking at he's doing a much more extensive uh, study of arousal and how it relates to resting state, apparent connectivity and all of that. And it's, from his work, it looks like it's very clearly there is a strong relation between arousal and low frequency oscillations. So that makes sense. I mean, so that paper is looking into the mechanisms and tying it to various things like, pupillometry and other metrics of arousal. Um, what we're seeing here is more of an epiphenomenon of that. Just that
Mm.
as you lie in a scanner for a long period of time, your arousal tends to decrease, and so that's going to cause a secular change in the strength of the sLFO signal.
Mhm.
Um, and so one of the comments we got back from the reviewers on this was, well, how could you expect this to happen, during a task, right? Because you're doing something. It's like, well, The task, as it turns out, the subjects who do this task report it as being pretty boring. So, this is not super engaging. You do have to pay attention to what's going on, but that's not the same as being sort of revved up about it. I could certainly imagine that one way to test this hypothesis is to give have people do a task that's much more arousing, something that will actually keep their attention. And this is consistent with what we saw in the HCP data, which was that 75 to 80% of people do have this increase, but some people don't. So some people, I don't know, can keep themselves entertained or stay engaged in the task or whatever. And so
Yeah.
as a result, they don't tend to breathe slower over time, and their heart rate variability does not change over time.
Yeah.
And
Yeah,
their
I could think of
sLFO doesn't
like
drop.
many. So yeah, if it's the CO2 reflux is the primary mechanism, then there's an easy mechanism. It's just a physical mechanism. Could be the size of the person in the bore, the ventilation that day. Who knows? If it's primarily blood pressure, and you have 25% of your subjects are marginally more anxious, either they've got exams or a new girlfriend or whatever, and
Mhm.
they're occasionally getting adrenaline dumps, then there's a blood pressure shifting. So there's all kinds of ways that you could get 25% different responses from 75.
Yeah. Yeah, and so the obvious next thing that we want to do is we want to look at this in a range of different populations
Can you
because the
measure
is all
independently? So maybe put you've got a biopack, or you've got other ways of sampling the
we
air
do.
with the bore. So
Mhm.
rather than taking it from the person, take it somewhere above where they would be breathing from, sample the air and see if the CO2 level is changing meaningfully. That would be easy. Can you measure blood pressure easily in the scanner? Not easily. In a
Um,
press machine.
yeah, we have a non-invasive blood pressure machine. We could measure it every minute. We can't. We don't have it. Well,
So a
we do have
cuff.
a FiniPres. It doesn't seem to work in the
Okay.
scanner. I mean,
Okay.
we bought it to work in the scanner, but if you attach the 10-meter hose to it, it just never fully calibrates properly. That's probably
Right.
we could probably just send it out to get fixed.
Right. Okay. Um, so the perfusion, I'm wondering if there would be a way to just measure perfusion pressure as a surrogate rather than measure the whole blood pressure. I wonder if we could do it with like a sensor on the neck. Do that put the pulse wave velocity idea. So
Mhm.
do one plethy on the ankle, on the whatever that vein is that sticks out next to you.
Popliteal vein or something.
Yeah, the one I can point at that is right next to your Achilles.
Mhm.
That will be sufficiently far away and have a long vascular distance from. You could put one on your groin. I think we even tried that experiment just before the pandemic. We were trying to do that as a blood pressure measurement,
Mhm.
or a pseudo blood pressure measurement. But anyway, yeah, there might be ways to get at that. If blood pressure turns out to be a big deal, then we
Well,
would need
we
a
do
way.
actually have a project that I was doing with a visiting scientist, where we're trying to do PPO measurements at different parts of the arm to try to get the pulse wave velocity that
So
way.
what under the arm will be good, right?
Mhm.
And then where'd the other one be? Just on your wrist?
Well, we were doing it on the venous side, so we're doing on the wrist and then further up the arm.
Okay.
So that'd be venous return, but I mean, it's got a
Isn't there a venous return under here too? Does
there
that
is there
does that have
is.
to be the same vein?
I don't know. Um, we were working with a sensor we had, which is sort of a wrist-based sensor. So we could put multiple ones of them up the arm.
Right.
Um,
But aren't you trying to find the descending pulse wave anyway? Isn't it the arterial wave that you're primarily interested in? Isn't that
yeah, I mean that yes. Um, yeah, and we could get that. I mean, we have other ways of trying to get at that. We haven't looked at that very carefully though.
right?
I mean,
Well,
the
then maybe
FiniPres
the
the
FinoPress would be
FiniPres
the way
should
to go.
work well too, but it's just we haven't gotten that fully working.
Does FinoPress work on a toe?
It should, yeah.
Because maybe that'll help you a little bit if it's not working as well in the MRI. Maybe if there's a sensitivity to movement in the field or something.
It's not that. I mean, it's all pneumatic. It's basically you got this little Tygon tube that's 10 meters long, and you're measuring sort of
Oh,
oscillations in pressure in a little diaphragm at the end, and I don't know, just doesn't propagate well through the tube or something,
okay. So
or,
yeah.
or the tube leaks.
Okay. Okay. Yeah, yeah, like my old biopack. Okay, well that makes sense. Okay, cool. Well, that's fascinating because that's super important for people. Um, yeah, that's really important to understand and people to know.
Yeah, so I mean,
Interesting.
the way we're looking at it is, yes, I mean, this is going to make a this is going to have an effect on anybody, anybody who's claiming to make, that conductivity means something about the brain. I mean, I believe it does mean something about the brain, but I mean, this is a complicating factor,
Yeah,
you know. And I think it also has a second order effect, which we're looking at exploring, but I think this may also, and as we all know, as a result of some of the studies that were done, years ago, that you need to do 10 minutes of resting state fMRI to get a stable signal. I think after 10 minutes, the noise stabilizes in such a way that your measurement doesn't change as much.
yeah,
Um, so one of the things I keep meaning to do, and we'll do this pretty soon, is every single one of these experiments where they say, okay, well, we'll start it, we'll take a super long acquisition, right? We'll take 30-minute acquisition, and then we'll say, okay, if we take the first 5 minutes, how much, what's our connectivity look like? We'll look at, for 6, 7, 8, and the connectivity increases and it stabilizes. But what would happen if you took the last 5 minutes and then the last 6 minutes and the last seven, and did it backwards? Would your connectivity decrease over time? I'm betting it would.
that's a good hypothesis. I like that. Yeah,
Because you
the
wouldn't
whole
even have to take any more data, right?
yeah. And the 10-minute thing, I've always thought that this was just that's about the amount of data you need to average the fluctuations in minute ventilation and other things that are driving these sLFOs. That's about what you take to drive them to some nice, happy sort of trait and state mean for
Mhm.
the current session. But then, of course, if you've now got an ongoing background shift on top, then you have a time scale that you weren't aware of. But I think
Yeah,
there's
and the
nothing
thing is,
magic about that 10 minutes. I just think
all,
it's
all of those effects that you want to stabilize have that I think they drive the noise far more than I mean, neuronal
yeah,
connectivity. Why would they drive neuronal connectivity on that time scale?
yep, yeah,
They shouldn't, right? They are noise that's on top of what you want to look at.
yeah.
So, we're very interested in optimizing. So, one of the things I've been doing now is optimizing Rapidtide for noise removal. So, my interests with Rapidtide are primarily looking at hemodynamic properties because that's what I care about. Um, but despite my best efforts, people are going to continue to use fMRI to study neuronal activity. That's personal choice. I don't shame.
As you've
But
said multiple times, the neurons just hold the blood vessels up.
exactly.
Right?
Um, and Rapidtide turns out to be extremely effective at removing this signal. Um, So what we find is that the connectivity, when you regress it out, you fit it and you regress out these sLFO signals. Your functional connectivity measurements they decrease certainly because you're removing the artifactual connectivity, but they stabilize. They don't change over time remarkably, or at least over the time scales we've been looking at. Obviously you have to look at this more carefully and look at uh, probably look at ROIs of interest rather than just global connectivity. Because what is global connectivity? It's probably not you're averaging lots of voxels and connectivity paths that have nothing to do with anything. So
Mhm.
you're smearing out whatever effect you're looking at. You should probably look at like what does the DMN do
Right.
over time? Does it do you get a stable measurement in 2 minutes if you denoise it? Well, I don't know. Maybe you do.
Mhm.
Um,
And I suppose also there are, presumably people are going to be interested in slow frequency experiments. Somebody's interested in presumably autonomic nervous system.
yeah,
So, to be able to differentiate between a purely vascular effect, if such a thing even exists, if that's even
right.
a meaningful statement, to separate that from some feed forward change from arousal or the ANS. I don't even know how. This whole idea of baby and bathwater. I don't see the edges
Yeah. Well,
personally.
that's the other thing that you have to be careful about. It's like so my group's always been we've been sort of hemodynamic hardliners. It's all about blood. Everything's an epiphenomenon of blood flow. It's clearly not true. And then on the other side, there's everything is neuronal, and
Yeah,
that's clearly
also
not true.
not true. Yeah.
And there's lots of experiments that show. You know, my first response when I see a lot of experiments about slow waves, slow neuronal waves, right, is oh, it's just hemodynamic whatever, misinterpreting hemodynamics. but that doesn't make sense. Like you look at the data, these are like, it's not just fMRI, it's people doing, calcium imaging, right?
Hmm.
So
Yeah,
that's not hemodynamics, right? That's actually neuronal activity.
yeah.
So there are slow neuronal waves. How do those relate to what we're seeing? I mean, one thing I've always wondered, and I don't know enough about it to really be able to say anything intelligent about it, is it possible that hemodynamic fluctuations drive slow neuronal waves? Because on the one hand, the body's an economical system, right? I mean, maybe the neurons are saying, okay, well, I got to do my thinking things, and then I got to do housekeeping. And if somebody gives me a lot more blood and oxygen, now's a good time to do more housekeeping, right? So I'll just increase, astrocyte activity or something will increase. Make hay while the sun shines. I've
Yeah,
got resources. Maybe I should be increasing my activity. And so the neuronal activity is going to be driven by the hemodynamic activity, but it's also going to then drive further hemodynamic effects, right? So it could be this sort of self-reinforcing cycle.
yeah, yeah.
Um, so
That
when I
makes sense.
say, that sLFO signals are non-neuronal because they come from outside of the brain. I mean, we see them come into the brain, right? They exist before they come into the brain. Doesn't mean they don't get reinforced as they pass through the brain because of the effects that they themselves cause.
Yeah,
Uh,
no, that makes sense. Yeah, well, and certainly, we know that with increased ventilation, you get BDNF upregulation and all that, hence benefits of exercise, right? So presumably there must be some neuronal effects at some level, whether it's measurable on a minutes, 10-minute, tens of minutes basis. That I guess we could test experimentally. But yeah, if you don't try to approach the problem as a holistic, you're going to measure the response in an animal, the whole animal, right? Then you're going to miss at least half the story. Whether you're all vascular or all brain, you're missing the complexity of the entire system.
yeah, so I mean, on the one hand, if you don't remove the hemodynamic effects that we see, I think you're going to get a distorted picture of neuronal activity. However, you will be removing effects of, as you say, autonomic modulation, right? And so uh, the question is, and then it's a question of timescales. It's like for certain things, I'm sure the neuronal timescales are short, right? There maybe certain things. Again, physicists, not biologists, don't actually know, but I could imagine that visual processing, for example, probably doesn't care that much about your autonomic state. So the connectivity between different parts of the visual cortex is probably not going to be changed by autonomic state. But other parts, emotional processing, I don't
Yeah.
know, those probably do depend on it. So if you regress that out using our techniques, maybe you're going to make something you're looking for go away. So obviously you have to be
and
careful.
and things like gut brain axis changes, other things that are likely to trigger, as you're laying down in a tube, right? Well, that's laying down. Your body doesn't know so it's time to digest and switch over to energy conservation mode, right?
Right.
That's what you do when you're laying down. It's nap time. It's digestion time.
Which is why in my copious free time, I think about things that I should do. And one of the things I think of is I should go hunt down the people with um, vertical bore uh,
Oh, phonar system.
fMRI scanners. I mean, there's one in Recon, right? So what happens if you're sitting down? Do you see the LFO increase over time if you're sitting in the scanner rather than lying
No,
down?
absolutely. Yeah, yeah, exactly. I'd also be curious to see what would happen if you had a blood pressure cuff and you released your blood pressure around the ankle or something, and you just around the calf, and then you give a pressure blood release, change the blood pressure, like would that screw things up? But there's all kinds of things that we could do
Mhm.
to interfere with the system. I suppose for the fMRI folks, if there are any left, they should be measuring this shit. Don't be waving your hands and writing discussion sections that are 5 times longer than your results section, which is always a red flag, right? I don't understand what I'm doing, so send more money. I'll keep scanning. But if you have a way of measuring blood pressure, if you have a way of measuring arousal, if you have a way of the gut response probably a bit too ambitious, but at least we should be measuring the sort of the headline parameters, surely, if we want to understand what the entire organism is doing. And then it's about explanatory power. It's not about, you can tell stories all day, but it's which of these signals, because they're signals, not noise, which of these
Mhm.
signals is telling you the most about the state of the organism right now.
Right.
So, all right, well, maybe I need to get back on my soapbox, try and find somebody who's doing a little bit more of this, because I think we're just, I mean, some people measure pulsatility, finger uh, pulse oximetry. Some people do chest motion. I don't know anybody who does any more than that, unless they're doing a breathing gas experiment where they're doing,
I
they
mean,
want to measure CVR.
Jonathan Power does a lot of stuff monitoring,
But
rare
he's always got a face
respiratory
mask
events
on.
and stuff. Hmm?
Yeah, but he has a full face mask. That's right. That's right. So he's trying to measure all of that stuff. But I don't know that he's is he also doing pupillometry or some other arousal measure?
I
Probably
don't
not.
know. I know he was doing a thing where he was trying to extract this data retrospectively out of HCP data, identifying rare respiratory events and then using that to. Uh,
Well, there's the optimist's angle. If we can figure this out, if a few of us can figure this out, it might be possible to then derive some data-driven method to pull these signals out and interpret them properly, right? Like you've done with Happy for cardiac,
mhm.
right? Or even Rapidtide for sLFOs, right? You don't once you know it's there and once you can interpret it. If you have a model, then you can interpret it. You don't necessarily know exactly where each of these come from. The heart rate pulsation is pretty easy, but the sLFO we have at least three candidates, and it's probably all of them.
Yeah.
But in principle, if you knew a bit more about arousal and you had a model of what the gut does when somebody lays down, you would be able to then figure that out and disentangle that from other slow wave changes.
Well,
And
we had this discussion, I think, during one of the discussion parts of Finding Hemo, I think I mentioned, we were talking about physiological monitoring and what sort of physiological monitoring should you do. And you can think of all manner of things, galvanic skin response, respiratory rate, end-tidal CO2, end-tidal oxygen, all of that stuff. Uh, all of those explain some of the variance in the signal. And at some point, maybe you can explain 100% of the signal and you don't have to put people in a magnet.
yeah, yeah. Well, I mean, or you're then able to if it's always messy and there are no hard boundaries between anything neural and vascular,
Mhm.
then these boundaries probably not even static anyway, or the overlaps are probably not static. They probably move a lot depending on what the organism's trying to do. So, but yeah, at least you would have a mechanism to tell a slightly more nuanced story rather than it's these neurons talking to those other neurons and there's a network of blah, right?
Right.
So I don't know.
I mean, there's something to be said for a reductionist view in order to like solve specific problems, obviously, but the brain is just, it continues to be more complex than we want it to be. Well, I mean, it's
Too
nice that
bad.
it's complex,
Yeah,
but
too bad, people. Too bad. Suck it up.
yeah.
So I read a paper recently on sommeliers because I have no interest at all in wine. That was
More
actually out of
different.
BCBL. There was a BCBL study. You mentioned
Oh, okay,
BCBL,
yeah.
earlier. And so I went straight to the experimental design because anytime I see anything to do with swallowing or sniffing, I'm thinking, yeah, red flag, confounds, right?
Mhm.
Let's see um, how this shapes up. But it was interesting. I mean, I don't have any direct things to say. I'm going to see if I can get one of them to appear on here so I can poke them about it. But that's a very long-lived, very subjective, very sort of whole brain task. Not so unlike watching a movie, right? It's
Mhm.
a different type of stimulus, but it tends to drive lots of things like all kinds of visual imagery and language, etc., etc. But with the added confound that you've got to swirl it in your mouth or smell it or whatever, and that we know is going to start to have some other effect in your scan data. So I don't know. It's people like that I think that really need to start to think more um, carefully about measuring all of the things that you can measure. I was thinking, like in terms of sommeliers, I would put a sensor on where I don't know if they did a comparison between the two groups, the naive wine drinkers, the amateurs, and the sommeliers, to
Mhm.
see whether there was a systematic difference in the motion parameters between the two. Presumably not, or they would have flagged that because they had it as
Mhm.
a regressors of no interest. But I think I would still be skeptical, and I'd want some additional measure of movement of the throat or something. I'd want a plethy or something on there to give me an independent measure. Right? I'm just not. I can't assume that the measures that I'm getting out of the brain data are everything that I need to know about the system, just in case. The professional sommeliers are much better at moving things around in their mouths and swallowing carefully.
Yeah, well, it's
Right?
possible.
So anyway, that was another thing I wanted to ask you. Did you ever resolve the issue of SMS versus conventional multi-slice for Rapidtide?
Uh,
Is there ever an
no,
answer for that? Because I know there's loads of different parameters that change,
right.
including especially resolution.
Yeah, no. I mean,
Okay.
you certainly can get good rapid tide data out of SMS data, but it does seem that some of our best results were out of sort of bog standard, 3.5 millimeter 3.5 millimeter isotropic, 1.5, 2 second TR data. Now, part of this may just be that, you know, when you're doing SMS, you tend to go to smaller voxels, and the
Yep.
signal to noise in the individual voxels just goes way down.
Yep.
So maybe we should just be filtering a lot more than we are.
Yep.
But I'm not exactly sure. I mean, yeah, as I say, you certainly get good data, but it sometimes can be weirdly patchy. And I don't
So
know,
you have
I'm
to
not
do
sure whether.
despeckling more because you've got some occasional weirdness. A
Yeah,
lot more voxels too, of course. Many, many more.
you got a lot of, yeah, you got a lot of voxels to deal with. Each of them is small, but in a lot of cases, it's not so much that the signal to noise is low. When you look at the correlation functions in these voxels, and they look good. They don't look, they look like a correlation function, but they'll be like these weird baseline rolls. So if you look at it, you're looking at a bunch of voxels and you say, okay, that's clearly where the delay is, right? You say the delay is here, delay is here. Okay, next voxel over, the delay is here. But you look at the correlation function and they're almost indistinguishable. It's just that there's a baseline roll that's made this peak over here to jump up a little above this other one over here. And
And that comes from the autocorrelation generally, more
yeah,
often than
well, I mean,
not.
the fact that you have multiple side lobes comes from the autocorrelation,
Okay.
and that comes from just sort of the peculiarities of you happen to have a weird spectrum in your sLFO in that particular um, it's set of stuff. Yeah, I mean, one thing I've been looking at is what happens. I mean, because we've seen this thing with the uh, with the growing sLFO. Maybe you would be able, maybe if you're doing Rapidtide for time delay, you should just take the last 2 minutes or last 5 minutes of the data set, right? Because that's where the sLFO is biggest, right? Um,
Oh, that's an interesting idea. Approach it backwards. Yeah, yeah, yeah. Yes, okay. If you're just going to try
because
and pick
neuronal activity
both.
is noise as far as I'm concerned,
Yeah.
right? For that.
Right.
Um,
Yep.
and one thing we found looking at this data, and again, it's a little hard because of the signal to noises, but in general, it seems that while the strength of the correlation grows over time, the delay doesn't seem to change. The delay,
Good.
during any given run, the delay seems to be pretty stable. So if I look at the delay maps
Good.
over the 4 segments of an HCP run, the sLFO is progressively getting bigger and bigger and bigger and bigger, but the delay maps just look like the time one looks like a noisy copy of time four, right? The delays really aren't changing that much. So that's good. So that means that if you fit even for denoising, if you fit the delay and you in the last 5 minutes, you could still extrapolate back to the beginning of the time course in
Is
terms of
that true for anybody with pathology? That might be true for healthy.
I don't know.
What if you had your moya subjects in there and there's some sort of orthostasis, some sort of change in blood pressure, and then the vascular steel is changing?
Quite possible. I don't know. I don't have enough of that data.
I wonder if you could get some. Oh, okay. I wonder if you could get Manus's old data and just look at that now that you have a new hypothesis. If you have any long runs, presumably you'd need how much when you say
I mean, the
longer?
thing is, with most of Manus's data, he's doing the carbogen challenge though.
Oh, right. Okay. Yeah, that's no good. So,
Although
so
Yunji has done some stuff where if you regress out the gas challenge, the the native sLFO is still there, and it does not,
oh,
it shifts a little during the high CO2 times, right? Because you're doing the vasodilation. I think you will change the blood flow. I think you slow it down actually, because the vessels are bigger. But even on top of this enormous, 5%, 10% variation in bold intensity, you see that the sLFOs are just kind of wandering around, and they're down at the bottoms of the peaks, and they're down
because
the tops of the bottoms. But it looks like a fairly continuous wave.
so the SaO2 could be the main driver of those SLFOs or blood pressure. So maybe it's yeah, maybe that just gets the mechanism. It's just you're biasing towards one big. You're taking one of the conventional origins of sLFO. You're hijacking that, using that for something else, but the other two are still
Yeah.
operational.
Well, we do have a data set where we did resting state with breathing air, and we had it breathing. So we did gas challenges, but we also did resting states where you were just breathing pure oxygen, or where you were just breathing 5% carbogen. Um, and this is a complicated data set because even though we randomized the order of all these things, it turns out it takes a long time to wash out CO2.
Oh yeah, minutes.
So yeah, so we probably
Mm.
did not leave enough time between these to get clean differences. But one of the things we found is that in terms of running Rapidtide, it didn't work so well in the pure oxygen cases or in the carbogen cases. And that may be because you've sort of pushed the system out of its linear regime of responsivity to CO2 changes, right? So either you're clamped way down, um, or you've reached the capacity of your vessels to expand in response to CO2. Um, and so the low frequency fluctuations that we're looking for don't show up very well. But it could just be that the data's bad.
Yeah.
I don't think it's that, but
You reminded me just now when we do breath holds, for to a 30-ish second breath hold, you need a couple of minutes to go back to baseline, but you never
right,
truly get back. The baseline does drift. So
right.
that would also go right back to your concatenation of your long runs and your baseline drift in sLFOs. If you're laying down for long enough and just normal breathing, but you occasionally and your arousal's going down, and then your ever so slow, your respiration rate and depth is going down, so you're blowing off less CO2. Chances are your CO2 level in arterial CO2 is going up slightly. So that would definitely
Yeah.
be a contributor to this stuff, because it takes minutes to
Mhm.
big deep breath, but you might get back to normal, but it takes a long time. Um, all right. Are you still doing any of are you using your dynamic GSR for denoising? Is that still what you recommend for fMRI folks
Yes,
in
yeah,
one paper? Okay.
yeah. So that's
No change there.
and so I've actually that's been one of the major, as I say, that's sort of in response to what we found in this paper. It seems to us more important that you need to do this. Even though the strength of the LFO changes over time, you can just fit it in one go and remove it, and it does remove the data much more effectively than any of the other conventional methods. Global signal regression does take some of the signal out from it takes it out perfectly from certain parts of the brain, and then makes it worse in other parts of the brain.
Yeah.
So I've been trying to optimize Rapidtide to do the denoising task easily. Now there's a denoising flag. So you say, it's like Rapidtide input file, output file, minus minus denoising, and it'll make intelligent choices about what it should do, and that should make it easier for
And it's
making
and
more
it's doing
accessible.
that on the full time series, right? So for a voxel, the full time series of that voxel, you take out what you think is the sLFO for that time series for that point.
Yeah. So what you do is you calculate the
At
time
the
delay.
appropriate lag.
Yeah, you calculate the appropriate lag for every voxel, and
Yeah.
then you take the assumed sLFO regressor, delay it by the appropriate amount, and regress it out of everything. out of every.
once per voxel,
Yes. So you are making an assumption that there is one pool of delay per voxel.
which is not unreasonable.
Yeah. I mean, it's not, yeah. It works pretty well. It's not perfect. One of the things that added a twist in, there's a couple things that are in the new version. Throwing in a temporal derivative of a time course excuses a lot of slop in time delay estimation. So if you regress out the sLFO and its derivative, you probably would get slightly better noise removal. And again, you're only burning one more degree of freedom, right? It's not a big
Yeah,
deal.
and that's fair because then if you have changes in in arousal, if you have respiratory sinus arrhythmia, etc., you'd expect some sort of acceleration component,
Right.
some dynamics to the dynamics. So that would make a lot of sense. I think that's probably a smart thing to do.
Yeah, so it's a secret option in there at the moment. I haven't yet rolled it out, but it's um
I wonder if okay,
because
go ahead.
this actually, because in response to the review for this paper, one of the reviewers asked, well, why don't you just do, well, there's one reviewer, I think they were, why don't you do global signal regression? Okay, that's fine. We show why you've probably, that's not enough. But people are, what happens if you add in, white matter regression? Because that's something a lot of people do. And one thing that we've found is that the white matter signal is basically the global mean signal with a 3-4 second delay on it, right? So then you get two bites of the apple, right?
Yeah.
You get two different time delays. That will give you better regression, that will give you better noise removal. So I did say, well, I did think, well, what if I just take the global mean signal and its time derivative? Maybe that's enough, right? And the answer is it's better than just doing global mean signal regression, but it's not as good as doing the full regression because even in healthy subjects, you have about a 6 second range of delays that you get in a healthy brain, and putting in the
Between gray matter and white matter.
well, I mean, yeah, between the earliest of the gray matter and the latest of the white matter,
Okay,
and
yeah, makes sense. Yeah.
And as I say, it's better. And I've done a bunch of simulations. I was thinking I was going to make a Jupyter notebook trying to demonstrate why you need to do this in each of these ways. And if you look at it, you get much better noise removal than you do with just doing a single time course. But still, at the edges, as you get out to -2 or +2 seconds, it's not as good. You're not removing as much noise as if you actually delay to the appropriate amount. So if you did global mean signal and white matter regression and each of their time derivatives, you'd probably remove more. You still would do better, just finding the correct delay and regressing that out. Especially if you have pathology, because if you're looking at somebody, this works okay for young healthy controls, but as you get older, normal healthy older adults have a lot of pools of blood that are delayed, 5 seconds, 10 seconds, and doesn't seem to have any ill effects. Just seems to be getting older. You build up cruft in your various, in your various vascular territories, and some vascular territories are just going to be later, right? And so global mean signal plus a time derivative is not going to remove noise properly from them. So you're going to get this weird systematic biases in certain parts of the brain. You don't want that. So
going back to the SMS issue for a second, you might have just stumbled upon a good explanation for why resolution makes so much difference, because you've got partial volume effects. It's a big deal in ASL, right? It's one of the biggest variables in ASL is just simply not having enough spatial resolution to separate gray matter from white matter, and then you just get the smallest amount of movement or scanner drift will cause you to fall one side or another of a boundary, and then you get a very different result. So that would still be true of sLFOs too. When you've got a potentially up to 6 second difference between the gray matter on one side of a boundary and then the white matter adjacent to it. If you have a big voxel, you've got the volume average of whatever that is, right? And it looks like a stable number. But as you start to get down towards something where you're separating these two, now it's bistable, right? So now it looks a little funky. And it could
that's true.
even
I mean,
be
it could be that as you go to smaller and smaller voxels, you're revealing the true heterogeneity that's actually
I
there.
would think there'll be a transition. So you go through once you go beyond, once you're clearly able to characterize this is gray matter, this is white matter, then at that point, I would expect things to stabilize again, assuming enough SNR, right? So it might, I'm just wondering that we should be able to test this. So this is just a partial volume thing because that's, I know that I'm on high alert for that for ASL. It seems to be one of the biggest sources of variability in ASL. And related to that, you could imagine too, if you are in, let's say you're in gray matter, and you know you're in gray matter, but you've got the point at which you're considering happens to be influenced by two distant large draining veins. That's also going to be a weighted average. And
That's
so,
true.
right. So again, if you can subdivide, it's another partial voluming effect, but it's just a slightly different effect because it's through space. But we know,
Partial delay effect.
yeah, right, yeah, exactly. So I can now, yes, okay, I've got to think more about this, but I can imagine there are all kinds of interesting effects from increasing the resolution. So it might not be an artifact at all, it going to SMS. You might actually really be seeing more of the true underlying variability that you've convenient, just like with global signal, it hides a lot of sins averaging
Right.
across the whole brain, but it doesn't mean it's correct. All right, well, I'll have to give that some more thought. So, so dynamic GSR, I'll put the links down so that people can go look at the other one paper and it's all in Rapidtide, right? So they can just adapt
Yeah.
that, put it in their pipeline in a way that
Yes.
fix, denoise.
Yeah, there's a whole, yeah, I mean, there's, Fix is good. Fix does wonderful things. But Fix and Rapidtide fight in a way that is unseemly. Basically, Fix removes a good portion of hemodynamic noise from certain parts of the brain in a way that makes Rapidtide not work properly if you try to run it on fixed data. Because
Mhm.
you got big holes and like the superior sagittal sinus region is a region where we actually pick up an awful lot of our signal when we're estimating our sLFO, but Fix nukes that, right?
Is it
So
doing it like an A comp core? Is it doing it like a what white matter
well, I mean, it's looking.
regression?
It basically it classifies a whole bunch of components, right? You run ICA, you see a bunch of components, and then you've recognized certain ones of them as being bad. Certain of them have been tagged because they have, they're they're things you typically see when you have a motion artifact, rings,
Mhm.
sort of stuff. But then
Yeah.
there's this back of the head, sort of the little skull cap at the back of the head, which is right around the veins going into the superior sagittal sinus. And that is tagged as I think it's, I don't know what it's called. They have different classes of things. It may be called cardiac because it's clearly a blood driven signal. And that's just a really big, rich, uniform area where it's great to fish the sLFO out of if you're trying to do a refinement operation. But if Fix has already nuked it, then
This is
you
the
know,
whole.
yeah,
Does
then
it just produce
at
a
disadvantage.
disconnect? So you're
Hmm?
propagating along happily, happily, happily. Let's say you're going from internal carotids forwards in time. Let's say you seed in, you get to the point where this would have the blood would have otherwise gone through this point. Oh, there's no signal here. Avoid, and that's it. You lose everything from there forward.
I mean, I haven't gone into it in that level of detail. I've just tried to run Rapidtide on fixed data a number of times, and it sometimes it works fine, but a lot of times it loses the thread of what it's doing, and it can never find a starting regressor that's good enough. Um, so
Oh
one thing
well,
you
not
can
even from
do,
the global mean.
right, well, yeah, because the global mean is dominated by blood signal, right? And
Okay.
the SL the superior sagittal sinus signal is a large um, is a large contributor to that. Even though it is delayed relative to the rest of the brain, it still helps build up the signal. It
Right.
acts coherently into the GS, into
Right.
the global mean.
Right.
Uh, so what you can do is you can just do them out of order. So what we do when we're processing HCP data is we use the minimally processed data that hasn't done fix, run Rapidtide on that, get all the delays, and then we use that to denoise the fixed data, right? We said, here is the sLFO in every voxel, take the fixed data and regress out whatever you can find of this from the fixed data. And that seems to work pretty well because,
Okay.
I mean, they
Okay.
are linear operations. They're supposed to play nicely together, right?
Mhm.
Uh,
Well, yes, and also you have a principled method to take to understand something with Rapidtide first. You can always then go and run fix if you can find ICAs on whatever's left. It's like there's always a reason you can do that.
yeah, I mean, ideally, what you should do is you should run Rapidtide, and
Yeah.
then you should run fix de novo, It's just, it's complicated and I don't want to do that. So I'd rather take the fixed data that the HCP has already done for me and try to,
Mhm.
try a correction operation on that.
Mhm. Yeah, that always brings me back to this whole drift, the LFOs increasing over time. We've known that the noise is pink, right? 1/f for forever, right? In fMRI, and everybody's always pointed at the scanner, which might have been true, I guess, perhaps 20 or 30 years ago,
Yeah.
right? Scanners were unstable, but now scanners pretty stable and they'll get into a temporal steady state pretty quickly. And so I wonder if it's a convenient way for the fMRI crowd to ignore the problem. It must be the physicist's fault. Your scanner drifts. No, in fact, no. Maybe it doesn't. Maybe it's your subjects that drift.
I think it partially is. Yeah. I mean, certainly, I mean, you will see 1/f noise in a phantom, but not to the extent that probably that you see it in humans.
Well, right. And also, the 1/f noise that I'm used to seeing in a phantom follows exponentials.
Right.
The time courses are almost always exponential. So, because you're following real physical properties, right? Heating, cooling, right?
Right.
So that should do that's actually worth remembering when we start to look at these things. We should be able to understand a lot from the shape because there are very few drifts in the scanner that are not exponential, as far as I can tell,
Mhm.
unless it's something so slow that it would be linear over the course of
Well, and
days.
even the sLFO growth has got to be at some point it's got to roll over, right? It can't increase forever. Um, at some point
No,
you're
it should hit some asymptote. Yeah, right.
yeah, because your breathing rate has, if your arousal is going down at some point, I mean, you're going to continue to breathe, so it
Mhm.
can't go to zero, right? So,
Right.
um, uh, and we do see when we look at if you look at the sLFO over one of these 14-minute HCP runs, you can convince yourself it's starting to roll over at the end, but I wouldn't put money on it.
Anyone looked at that the same characteristics in EEG, either within the MRI scanner or just laying down? Maybe the sleep folks see something similar in the EEG.
Don't know. Um,
I'll ask my guys, my sleep guys,
mhm.
if they looked at that. I'm going to do a quick literature search.
I mean, one of the data sets we did for the paper is a sleep data set, and you do see this even in subjects that are sleeping. Again, it
Well,
seems
but they were they,
but again, it can't go on forever. So
but they presumably they're awake when they get in, right?
yeah,
And they
that's
fall
true.
asleep, and then so it's drifting, drifting, drifting. It just keeps drifting, and now they're asleep. It's just
Yeah,
drifting, keeps drifting. How long did you measure for?
I don't recall. I mean, I
If it was drifting at the end of an 8 hour night of sleep in the scanner, that would still be, well, that'd be
oh
crazy.
yeah, no, I don't think it's that. I
Okay.
think these people are sleep deprived so that they fall asleep pretty quickly when they go in the scanner. So it's not like I don't think they've been sleeping in the scanner all night.
Right. Okay. So then that's where I would expect to see the
Yeah.
asymptote. Okay. Cool. All right. What else you been up to? Any other exciting discoveries or artifacts for me to think about? I only like problems.
Um,
I don't like things that work.
I don't know. Nothing comes to mind right now. I mean, we have been working for a while on trying to figure out ways to actually modulate some of these signals directly. It's like I'm tired of doing read-only science. I want to write something. As you say, like those blood pressure cuffs that
Yeah.
you can release. We've actually we're looking at active modulation of blood pressure
Good.
with cuffs and stuff. It's yeah, well, I'm glad you like it. The NIH didn't.
Oh, stuff the NIH. They'll be, well, that's our colleagues. It's not the NIH. We blame the NIH.
Right.
It's people who you talk to on a daily basis who decide that when it's time to give you money, no.
Right.
So
We're going to do it anyway. So
yeah, good. You know what I came across the other day, which I'm still thinking about? Noam Sobel came up with a thing about 3 years ago called the odor hood. So because he's olfactometer guy, right? It's olfaction, and they've always had problems with nasal cannulas and face masks, same as we have for just breathing gases. So they've created this like entire like little mini greenhouse for the head coil, so they can puff odorants in in super quick time, like 150 milliseconds, I think is latency. And I was like, oh, that's cool. Because then you could control the environment with things like you could surreptitiously modulate the amount of CO2 going into the subject's breathing. And you could put any other, when you're doing these long, slow experiments, you could put some really complicated, damped sinus, undamped sinusoid in, whatever you want, right? And just where you have a unique trace, you could even change the O2 if you
Yeah,
have permission to do
that's
it.
true.
That would be neat.
Yeah, I've always wanted to do pseudo-random modulation of CO2 using a respiractor. It's try to get some sort of
I'll save you your money. I've got a plastic bag here and there's some tube. And we'll pay an undergrad to twiddle the knobs. We'll give them a script to follow, increase in this one, decrease that one, and just put it into the scanner. A $10 solution, and we just won't ask for permission. We'll just do it.
Yeah.
I'll do it on my scanner.
Okay, I'll come by. Yeah,
That would be super interesting. Oh my God, that's really, really, I got to think more about that because that's exactly the kind of thing that I think because I worry about reflux. I've always worried about reflux in the scanner. But yeah, this kind of stuff where you're making very small changes, right? They're not going to be life-threatening. So
Right.
you're not clamping something on their face. You're just changing the whole environment.
Right.
The person has no option but to breathe the environment that you're putting over them. I'll dig that paper out and see if I can invent something. So what else? Blood pressure. How are you going to modulate blood pressure? Just with a cuff?
Good
Just
stuff.
okay.
Yeah, cuff and Arduino, some pumps. It's I have a prototype. It's actually kind of cool. It's
Neat.
come by, I'll hook you up to it. It's a
Oh,
weird
yeah.
sensation.
Yeah, I can imagine. Well, that's the other thing. The one problem I have with that would be attention, right? It's going to be very hard not to attend to something releasing pressure in your thigh or whatever.
Right. But again, I mean, what you can do with that is if it's continuous, if it's continuous and running through the entire experiment and modulating in a pseudo-random way that you don't make sense of, but that is designed in such a way that it has good cross-correlation properties or
So
whatever.
yeah, so you pick a nice
Yeah,
frequency,
something that's
change
easy
the
to pick out of
frequency.
the noise. Because that's the problem is that a lot of resting state fMRI is like astronomy, right? You
Yep.
just sort of look and you get what you get.
Yep.
Right? And tasks, there's only so much you can, you have to go through the entire brain. But at least with direct blood pressure modulation, that's a little more direct. That's a little more of a sort of a classic DSP problem. You have an input, you have an output, you have a black box. If I design my input function properly, then I can learn about the black box. I can learn a lot about the black box.
Oh man, you know what? I wonder if we take Steele Noam's Oderhood idea, I wonder if that might help get your grant across the line. If we think about like holistically, make an entire system of ways to manipulate the environment of someone, ideally surreptitiously, right? Obviously, with blood pressure, less easy, but maybe this is good and trying to generate this orthogonality between all these different things that we know have a signature in the physiology. Maybe we can come up with something holistic. I'll think about it.
That'd be cool. Yeah.
But
Yeah.
don't
So imperceptible variations in gas
right.
concentrations.
Exactly. Yeah, exactly. Yeah. Just like, but the vision scientists and folks have been doing that for a long time, right? And changing luminance and things without you knowing, right? You think you're doing task X and they've actually got you doing task Y, but you don't know what task Y is because you weren't told ahead of time that in fact they're going to change the luminance on you and you're just attending for the cross or whatever it is. And that's a smart thing to do, right? We should be doing the same kind of surreptitious approach in physiology, I think, so that the neural stuff is. I mean, maybe actually subconsciously you start to perceive these things. That would be interesting.
Do a survey after and say, what did
Well,
you
you may
notice?
not know. You may never be aware,
Yeah. Yeah.
right? You may never be able to vocalize it. It's the gorilla in the suit. All right. Well, anything else we should before I stop the old record button? Anything else you want to tell the good people about? I'll make sure I got all lots of the links and things for the Rapidtide and the papers and explanations of what sLFOs are or what we think they are.
Yeah, we didn't really talk about happy that much. It does seem that there's an awful lot. Oh, Actually, there is one interesting thing I was doing. I'm interested in, I mean, you can cut this out later because maybe this is boring. Um, but some old data that I had, we had we did magnitude and phase reconstructions when we acquired the data because we thought it might be useful for something. I was looking at the data, and I did um, looking at the phase data, and I found that breathing shows up almost entirely in the phase channel. Um, and
Is that
which makes sense, right? Because if you think it's a susceptibility modulate, if you think the dominant amount of signal that you get is susceptibility modulation because of your lungs inflating, right? So that's going to show up as a pure phase modulation.
with
Uh,
very long length scale, centimeters?
yeah,
Yeah.
yeah. I mean, basically coherent over the entire head.
Yep.
And if you reconstruct that way and you sort of you just look at the phase maps, it's just like up and down. And but it's I was wondering if there's anything you can like anything intelligent you can do, knowing that no, if you know that breathing is a phase modulation rather than an amplitude modulation, does that let you remove it in some more intelligent way than you are currently? I don't know. I mean, maybe I mean nowadays we're all taking data fast enough that we can sort of respiratory motion is not as big a deal as it used to be. Um, I mean, cardiac signals, as far as I can tell, are primarily amplitude modulations, right? Because they're, you know, you know, God only knows what's causing it. I mean, there's some amount of, through plane, flow effects and small subvoxel motions and all kinds of things. But I think they mostly show up as an amplitude modulation. They don't seem to
That
show up
makes
much in
sense.
the channel.
Mhm, mhm. That makes sense. So yeah, so the respiratory, at least the component of the magnetic susceptibility component that causes the translation and
Mhm.
phasing code axis, that part would make sense as a phase shift because that's why it's translating, right? So
Mhm.
yeah, that's a good question. But you can always fix it just as a translation, right? As a virtual motion,
Right. Yeah. I mean, I'm just
which is what people do, but inadvertently, right? It just goes out with the rest of the six DOF regressors.
right. But what I did find is that I mean, there's an interactions clearly between the cardiac and the respiratory signal.
There better
Uh,
be. There's respiratory sinus arrhythmia for a start.
yeah. I mean, does that yeah, I mean, there's a coupling, but also, I mean, in terms of the signal that you get, like, do you learn anything knowing that it's a phase modulation of an amplitude modulated signal? Does
Mhm.
that buy you anything in terms of
Mhm.
how you might want to intelligently
Mhm.
figure out how to remove the interaction between the two? I don't know.
You mean like it, so you could potentially, well, I suppose you could potentially navigate it, do a phase correction rather than, and try and take that component out, pure phase correction, and then go back into amplitude mode. And then when you do your motion, let me say that again, volume realignment, no such thing as motion correction. That's
Right.
an aspiration, not a method.
Yeah.
So when you do your volume realignment, then at that point you would hope to be doing true head motion, not virtual shifts, right? Does that make
Hmm.
sense? So you could potentially disentangle those two rather than try and fix them all at the same time, just as brute force. I don't know there would necessarily be any advantage to doing that if you could separate it. I don't know. I'll have to give that some more thought.
I don't know, but that's one of the things I think about in the background. When I've got nothing to do, I sort of
Yeah.
tinker with that, and I see if I can learn anything deep. So far,
Right.
nothing, but
Well, if you could do a closed circuit, then you could potentially, if you could monitor that phase, you could do a slice by slice frequency update in the scanner. That's something I've always wanted to do because ideally you'd fix it in hardware, not try to post process it away.
right.
Right. I mean, if you think about vertical Bohr spectrometers, the NMRs, they have a deuterium channel and they just monitor where the field is going and lock it, right? And that's field frequency lock, right? Which we don't have. So, but we know we have an instability, right? And it's all deterministic, right? Everybody has lungs, and we know that. Well, anyway, something for the next generation of scanner designers to incorporate, perhaps.
I mean, once they've sold everybody a 7T, they got to have some new product to sell them, right? So,
Are you doing any 7T?
I'm not. No, we don't have a 7T. It does not seem to be in the cards at the moment. I mean, unless there were a donor who really wanted to give us a 7T. And if anybody's watching this wants to give us a 7T, you know, call me. But
You know
it,
what you do with it?
hmm?
You know what you do with it? Apart from they're very expensive beasts to keep.
They are expensive, and it's not. I don't know. I mean, for what I'm doing, 3T is fine. I mean, certainly it would be nice to see things at at higher resolution and all of that. But at least a lot of the hemodynamics um, is fairly, low frequent. It's fairly smooth in healthy subjects. Um, I'm not sure what else I would learn from it.
I always wanted a 5T or Christian Bewley's 4.7 to go steal his. That's probably the only surviving 4.7, which I think is still going. But yeah, 4.7 or 5T, because you get so much benefit for everything, from for fMRI, spectroscopy, but without all of the engineering nightmare that comes along with a 7T,
Right.
right? And half the SAR problems, because 5.5 is 25
Well,
versus
if I could get
7T.
a Siemens one, I would.
Yeah, well, exactly.
I
There's a
don't think I
Chinese
would want a
company.
cobbled together scanner.
No,
Uh,
no. Apparently, there's a Chinese company that's been putting together a 5T scanner. That's a sweet spot.
huh?
Seems to me. I mean, I don't know. Someone should run the numbers, but it seems like if you could skunk works a 5T, how many 5Ts could you sell if it literally had been upgraded for a 3T? Same footprint, same push button, probably possibly even do some non. You could certainly do musculoskeletal. Whether you could do cardiac or thoracic, that's a different question, right? But you could certainly do neuro and musculoskeletal very well at 5T.
Mhm.
Um, whether that would really be a good workhorse,
Yeah,
because I just don't
would it
see.
be enough of a win,
Well, it'd be
Uh,
on the research side. Yeah, it'd have to be on the neuro side. I think you'd have to. You'd maybe this is something that comes down the pike if some clever person figures out phenotypes from MRI data with deep learning, and here's your trajectory for Parkinson's, here's your trajectory for AD, and then oh my God, everybody's got to have 0.5 millimeter cubic structural scans, and you're not going to do that on 3Ts. So
right. I mean, yeah. I mean, the problem is the sevens are already there, and the manufacturers are pushing them, and they're approved.
yeah, I know.
So
Yeah, that doesn't mean that the numbers are there. It doesn't mean that it's going to
yeah,
be any easier to. It won't make them any more affordable. I don't know what the numbers would need to be for them to significantly drop the price, but the cost of ownership is still ridiculously high,
yeah. No, that's true.
and the number of applications is relatively small at the
Yeah,
moment.
it's not entirely clear to me, given the 70s that are out there, they don't seem to be running 24/7. It's not like people are clamoring to use all of them.
Right.
Um,
Well,
I
I think
mean,
that, again, maybe it's just cause and effect. Somebody has to come up with something super compelling that you can only do at 7T.
well, I mean, one of these days, Spectro is going to be the thing, right?
Yeah,
Spectro is
right.
the peak of the future and always will
Yeah,
be, but
like exactly.
someday the
Right.
future will come, right?
Hot on
So,
the heels of fusion. Yeah, it's going to be laser fusion and your cold fusion and all those other. Yeah,
yeah.
right, right. I won't
I mean,
live
the
long
thing is,
enough.
I mean, once you get up to 7T, things like, I would think that, for high field stuff, proton, I'm not sure. I mean, sure, it's better, but I think the big thing is if you could, if you had some really compelling use for phosphorus spectroscopy, for example,
Or deuterium.
or
So a lot of
deuterium.
people doing deuterium now, endogenous deuterium. So that's apparently a new cottage industry. I don't know how much is going on in humans, but yeah. What's his name? Robin van der Graaf and other people are dealing with that. I'm seeing stuff come out of that. It's interesting. Yeah, I'm not super close to the literature, but it's interesting to see. But then again, I've been around this game long enough to be skeptical of anything. It's another way for them to get money to keep funding their work. Good for them, right? It was
Right.
going to be C13. It was going to be hyperpolarized T13. It was going to be, I mean, at some point you have to get
Xenon,
with it,
Xenon
really.
129.
Yeah, right. Yeah, yeah, yeah. So I did that in the 90s too. But yeah, I don't know. I mean, it's good research, but it seems like to be a lot of people fishing. And someone has to catch a fish at some point, or NIH is going to just turn the tap off.
Yeah.
We're going to need a phenotype.
It's
All right.
interesting. It's how it's so hard to predict where things are going to go. I mean, it used to be everybody thought spectroscopy was going to be the killer app, and like you look at the what the GE3X Signas or 4X Signas at least were, they were really good spectral machines. They could do all kinds of stuff, and they just kept taking the capabilities out because nobody was using them, right? Turns out imaging was more important,
Well,
way more.
yeah, right. Well, it's easier to do. I mean, you have to look at the cost on the backside. Look at fMRI. I mean, 95% of the work is away from the scanner, right? As
Mhm.
complicated and as expensive as it is to collect the data, well, you can always collect good or bad data with the same amount of work. If you put a little bit more work in at the front end, then you can collect better data, which makes the back end a little bit more productive. But still, the vast majority of the work and the thinking has to happen on the back end. It's things like how do you process your data, how do you do your statistics smooth and blah blah blah. So and with spectroscopy, it's at least that complicated. So there aren't that many people trained in it to do it. There's
Yeah.
not like you can just put it through a black box and push it. Whereas most imaging, clinical imaging, is pretty easy to do.
Yeah. Yeah, it's interesting. I mean, fMRI is I mean, after all these years, it's still not. I mean, is it clinically used for anything? I mean, all of
Yes,
the technology,
yes.
the
Well, I was rib
surgical
bandaging about
planning for
this.
brain surgery, right? But
Well, no, it's lags. It's hemodynamic lags. It's Ahmed's
oh, well, okay,
mid
yeah,
stroke.
yeah, okay.
It's not the neurovascular part. It's the vascular part.
Yeah.
That's yes. And Rachel Strickland and Molly Bright have done that incidental finding with their CVR. Right, they
Hmm.
found 20-something-year-old with Moya Moya. So yeah, there's plenty of there's now published evidence out there that fMRI can be useful for uh, for clinical apps. It's just not
True.
the way that people
Not for neurons.
assume. It's not finger
And
tapping or
all of the improvements to the gradient systems and the reconstruction stuff, all of that is now rippling down into making imaging faster. I mean, it's ending up being useful clinically for speeding up scans and all of
well,
that.
that's right, and that's quite clear. All you got to do is so hopefully somebody from Siemens is listening. Like the stupid carrying handles on my head coils, I'm being facetious. The neck elements, which were requested by every fMRI lab ever not. Right? I mean, like it's asinine to incorporate these two together. It just gets in the way. But that just tells you right off the bat who's driving this, right? And it's not us, right?
Oh,
So
yeah,
these
certainly.
faster gradients, etc. And I was trying to develop my new system QA the other day. So I've got mean curve, right? So I'm trying to do everything on the scanner if I can. So I've got first of all, there's no mosaic, right? You can view some things in mosaic, but you can't analyze anything in mosaic. I can't load mosaic view images into mean curve anymore. So now I've got to find this particular
Well,
slice.
now it's multi-frame, right?
It's just like, oh cow, and again, time series data are an afterthought quite clearly in Siemens's mind.
Mhm.
They just don't care. The fact that it inconveniences us, too bad, right? We are not a market driver for them, and I doubt we will ever be a market driver for them.
Although it's weird. I used to I felt, I don't know, 10 years ago that the research was not a market driver. Certainly they knew that, in the end they were going to be selling clinical machines. That's where their bread was buttered. But I think they perceived more value in making machines more research friendly, on the idea that people will develop cool things that will end up turning into products. And now I feel less of that. I feel that research is less of a function. I mean, at least with XA30, I feel that it is.
It's a big step backwards, I think.
Yeah, there's much less of attention to, I mean, I'm not going to say, well, what will make researchers happy? It's more like, what will researchers tolerate? Um, and the answer is, well, who knows? Who cares? Right?
Yeah,
Um,
right. Yeah, that's it. I mean, it was super easy to make the transition. I went from VB17 to B17 to XA30. It was a trivial step. Okay, I'd seen the dot cockpit. I played with VE11 a little bit, but it's intuitive. So as a sort of everyday interface, super nice, super easy, right? It literally took me an hour to get going, right? And I felt, oh, okay, I know what I'm doing here. It's pretty good. But yeah, when you start to get into the the bleeding edge that we would need to get into, then it gets much more complicated. I think things like the coil files are much larger now, much more involved based on just the manuals that I've seen. And programming, I don't know. I haven't broached that. I'm going to try and stay away from that myself.
what I've been told from people who have been writing sequences is that a lot of things that Siemens used to provide as source code are now just library, black box libraries. They don't want you messing with them. So it's harder to incorporate some features than it used to be.
Okay.
I know that
Well,
was
that's a good reason to. So Lana's been. We've got PulseSeq, so to go to a slightly different way and just take things. Just try and do it all yourself. Use your own pulse programming environment, interface to the black box as needed to get your data, pull it offline, raw data, and deal with everything offline. So maybe
Have you been playing with PulseSeq? Because I've been intrigued by it.
I've touched it. So Maxime did come to the site to us a couple of years ago now, and we're just trying to get it going. I just got a laptop to plug into the scanner. I mean, when I say we, I mean Lana. So she's gonna run point on that for spectroscopy, and then we'll see where that goes. But it seems like again that's probably just a numbers game. If a lot of people go that route because they have to, when everybody's running XA30, XA60, or whatever comes next, if you have no choice but to join this particular group of people or fight Siemens to try to get your sequences working, because eventually everybody has to upgrade eventually, right?
Right.
All the research sites are dragging their feet on the E11 as far as they can, but eventually they have to.
Yeah, well, our institution is they're super unhappy about having a Windows 7 box lying around.
Well, that's right. Well, eventually they brick, right? They're
Right.
unsupported now, right? So yeah, you can't have them on most people's um, uh, uh, infrastructure, right? They won't allow them to be as a liability for your institution. But eventually, it's like my very, very old iPhone. If it turns into a brick eventually, the stuff that you'd like, I hate to have to upgrade and pay the money to. Eventually, you're kind of forced to do so.
I mean, Windows 10 is already pretty much end of life, right? So they're going to have to move again soon. But
Right, right. Well, hopefully the biggest transition was to things like this. It's more of a philosophical shift on the Siemens side. Things like 16-bit die or whoever's driving this bus, 16-bit DICOM.
oh yeah,
Whether or not the tools um, to process mosaic images or even to export mosaic images, that's a choice. Siemens could have, so they could in future just decide
the way it was described to me, it wasn't a choice. It's not compliant with the DICOM spec, and they wanted to comply with DICOM 2.0, and so they felt that but I mean,
okay.
sure, if
Well,
Siemens said no, we're not going to do it, then
yeah,
DICOM
so they decided
standard
that
body's not going to.
the people who make the rules should be obeyed. Okay, that's one way to do it. But we're scientists. We don't have to be DICOM compliant,
Right.
right? If we're doing science. So okay, well, anyway, I'm sure I'll be retired long before this stuff gets resolved. So anything else you want to bitch about, complain about, or sell?
No, that's mostly what I've been thinking about. I sent you an email about reading
Thank you.
documentation. So
I did, yeah, thank you. I will get on to that. Yeah, we should restart our Tuesday morning chats. That'd be good.
yeah,
So
yeah. No, I miss you guys. It's that was fun.
I don't know what anyone's doing. I need to talk to Yunji about lymphatics. That's all come back on my radar for some good reason.
No, he's coming here at the end of the week, so we're gonna
Oh, he is?
I'll
Okay,
see him.
cool.
Yeah.
All right. Well, let me pause this recording or stop it.
Okay.